yes, so this time, this time I didn't start recording session from the beginning. So first we were talking about a new participant, Khabir from Peru. So he is starting with a basis 3 board with Arctic 7 FPGA. And now we went into reviewing homework. Yeah, but with homework reviewing session, like actually prefer people to do homework first themselves, like without looking into a recorded session with a review. But in this case, it's okay right now. So let's continue to review homework. 1 second. Yeah. Okay. So far we saw uh, 401 we signed and with overflow, and so Philip put it in this way, checking that both highest we have overflow if both highest bits of argument are 1, uh, but some is 0, or if highest bit of arguments are 0 and some are 1, which is like equivalent to my preferred variant. And my and my preferred variant is that we can simply compare those bits with equal operation and not equal, or instead of equality and non-equality, we can use not XOR operation or XOR exclusive OR operation. So some people prefer a different way of doing this. I personally prefer this one as more readable, but you can do it either way. So then, uh, we went into signed add with saturation. So if you have a signed number and like addition causes overflows, and you can saturate it to put a maximum number, or if locating two negative numbers causes like negative overflow, so that sum has a 0 in a signed bit, saying that this is like positive number, then we put uh, like minimum negative number, and for a 4-bit signed value, maximum positive number is 7 and the minimum negative number is -8. -8 because 1 0 0 0 is actually not -0 but -8. So in the integer numbers we have only 1 0, but in floating point numbers we have +0 and -0. This is just some for your information for the future. So now in a saturation solution which was put by Mike Kuskov uses bit operations like this. But I would prefer to put it in a way how Philip put it, which is like in this way. But here, like I would prefer to put if a no, this is actually just fine. Yeah, this is short enough. It's okay. So now let's see 404. Yeah, so we also have 0403, but I think Philip didn't do it yet. Okay, so now here here we are doing multiple way of doing shifts. So in Verilog you have a shift operation, and in Verilog you can just get a number which is input. Uh, 1 second. Why it, why it moved? For some reason changed layout. Ah, wait, screen sharing is paused. Why it's saying screen sharing is paused? So strange. I think I pressed something wrong. Anyway, yeah. So shift operation. So in the Verilog we have a shift operation. So here is a module which gets as an argument 8-bit value, and it produces 8-bit results, so from bit 7 to bit 0, and we can just use shift to the left with a 3, but we can also implement shift using slice and concatenate operation. So we can get a, we can get a slice of A from 4 to 0 and concatenate it with a 3-bit constant 0, which is functionally the same as shifting by 3. And many engineers to prefer to do it this way. You can also do shift using for loop inside or always block. But for loop here is not the same as for loop in software. Like in software, for loop means that you just execute one instruction after another. But here in hardware, we don't have instructions. We have just wires and logic gates. So what the synthesis tool does here, synthesis tool gets code inside always block. So like always block is just a block of code saying that if anything on right hand side change, you change things on left hand side, and it gets this for loop constant, and it simply unrolls it. So it put result 0 equal result 1 equal result 2 equal and so on. So you can just put a loop where you go through each bit and check whether this bit should be set to 0, or whether this bit should be set to I minus 3, so that bit number 3 will get value from bit 0 and so on. Yeah, this is like second way of using Verilog syntax. And the third way is using a construct called generate. And generate, one limitation of for loop inside always block is that in this for loop you can put only blocking or non-blocking assignments. But if you want to use continuous assignment, you cannot use this syntax, because with continuous assignment you cannot put continuous assignment inside always com block. But you can use a generate construct which allows such loop with a body which consists of continuous assignments and module instantiations. So here we can do generate, and then we can put inside assign and check that if I is less than 3, then we assign to this bit 3, and otherwise we assign I minus 3. So this is example. So now is the task. And in this task, we need to implement a parameterized module. So now we are not using a constant like 7,0, but we are actually using a parameter we pass to this module. So here, if you want to shift it to the right by S, yeah, this is correct answer. So we use shift right operation by S. Now, if you want to do this, yeah, but here we need to use a parameterized module, and we shouldn't use a fixed constant. We shouldn't use constant 3. We what we need to do here, we need to put not 3, but we need to put like uh, s copies of 0. And to put s copies of 0, you need to use a different syntax. And one, because this module can be instantiated in another module, and this s can be changed. So this s may not be 3. So you cannot really do it this way. And one way of doing it, what you can do is put it larger. So one way of doing it, you can use a special syntax to concatenate multiple bits, and this syntax is a square bracket s, and then in square bracket a constant. So you are saying here that we put s copies of 0, and then we concatenated with a bit slice which starts from n minus 1 and like ends with s at the right. But this is not the only one syntax you can do. There is alternative syntax. So let me put here alternative syntax. Let me open Google Docs.
What is the benefit of using so different ways to do that?
Oh, the benefit is in this exercise is just a way to show different syntax features of SystemVerilog, because this is like a trivial example, but usually you inside always block or inside generate, usually you write not only one shift, but usually you write some complicated action, and this complicated action is uh, frequently it's convenient to express in one or another way. So let me
Okay.
show you different syntax for this thing. So one so for this particular exercise, for this particular exercise, uh, uh, the right way to do it is to either use the shift or uh, this is another solution, but this is a solution in Verilog 2001. But you can, instead of writing this, you can also write the following syntax. You can use a type conversion. So you can use a type conversion. You can put S, and then like you can put a tick. Uh, uh, so which means that this expression this expression of size S. So you can also put ampersand. And this syntax was not accepted by Icarus Verilog in version 11, but this syntax is accepted in version 12. Plus, the syntax is accepted in all the professional tools like Synopsys VCS, Cadence SimVision, and so on. So basically, you can write it in this way using concatenation operation instead of shift. So now the question is that why don't you simply write shift? But suppose you want to write something complicated. You don't want to just shift, but you can use slice and put together with a multiple slices. And in such case, instead of writing like shift to S and then writing shift back to, let's say, H, you can simply put construction from slices in this way. And in this way, it will be easier to read. At least if you know the syntax, it will be easier to read. Yeah. So the problem with what Philip wrote is that suppose somebody instantiates this module with a different parameters, like he will not use S, but instead he will write something like write shift with n equal like 10 comma dot s 5, and then instantiate it with uh, r shift and put a yes. So if somebody instantiates this module with a different value of parameters, like s is not equal 3, but s is equal 5, then like Philip code immediately breaks. So because you need to put here uh, 5 and here 5, but Philip uses hard code instead of S. So the right way to do is in this way. Yeah. Okay. Okay. So example with always block and with always block and okay, let's see. Yeah, this I think looks fine. So I is more than s plus 1. You put 0, and otherwise you put I plus s. So if you look to the reference example, no, in the reference example, you should actually do. Oh, wait, maybe you can do it in a Philip way too. So I is more than n minus s. I is more than n minus s to the right. Wait a second. Here, Mike Kuskov wrote it. Oh, yeah. Mike is right, but Philip is not right, unfortunately. Because you see, if you go back to Philip code, and I think here it works just by accident. Because we are using 8 and 3 here, it just works with accident. So if you put let's say like n is equal 10 and like s is equal 2, it's not going to work. So now draw what is going on here. So you are putting here that if we put 0 to everything on the left. So let me draw it. Let me draw it using. I don't think drawing thing works here, but let's try. Yeah. So if this is like our number, right? And suppose like s is equal 3. So what actually Philip wrote, that if we want to shift this whole thing, we want to shift it to the right? So we want to make this bit to go to position 0. And then we want the last bit to go into position here. So we are shifting everything to the right. But what Philip wrote that like everything in this area with I is more than S plus 1 and S is equal 3. So S plus 1 is 4. So everything left from the bit 4 is set with zeros. You see? And for I less or equal to S, we just put I plus S. But instead, we should do something else. So instead, we should do something else. So like I to S is correct. Like I plus S is I plus S is correct. So we are shifting to the right. Wait, but why is I plus S? Shift unsigned input by S bits to the right. Actually, this is not right. I think it should be I minus S. Yeah, I think this is incorrect solution. I should talk to Mike Kuskov that here we should put I minus S. Yeah, but we should put 0 if our bit from the left, which is n, up to n minus s. Okay, now let's see. So why it works. Yes, I need to review the thing because I think the solution of Mike Kuskov is not correct. I need to recheck it. Oh, I minus s. No. Sorry. Everything is all right. I plus s is like I plus s is correct. So we are getting a new bit 0. We get a new bit 0 from a bit 3. Yeah. So everything is correct. Yeah. So our new bit 0 of our result is coming from bit 3. So we are getting bit 3 and we are putting in bit 0. But the only difference is that, so Mike Kuskov wrote everything correct. But if you look to, so let me put different share. But if you look to the condition where we put 0, we need to put 0 for all bits with the index more or equal than n minus s. And Philip put it with the index with the index s plus 1. And this works just by accident because n minus s, when n is equal 8 and the s is equal 3, in this case n minus s is a 5, right? So and so n minus s is a 5, so like I is more or equal than 5 is numerically same as what Philip wrote, that like s is 3, so I more than 4, which is the same as I more than equals than 5. So this is going to work with these numbers, with n equal 8 and s equals 3. But if you change these numbers, it will get broken immediately. Yeah, okay. So same thing is here. So you can do it using generate, and so Philip wrote s plus 1, but actually you need to write here I is more than n minus s. Yeah, yes, and everything like everything else is correct. Okay, 1 second. Now with the circular shifts. So circular shift.
Are you intending to still show the drawing stuff, or go back to the code? Because I thought you're
I can show I can show drawing. Like I can show drawing here. So let me share drawing, and I will show what is circular shift. Yeah, just with such thing, just with such exercises, you need to really carefully see what bit moves where. So what is a circular shift? So like in circular shift, if you have some like number here, so like 1 0 1 1 0 0. So with a circular shift, if you uh, do circular shift by 3, like this means that this bit 0 shifts here, shift by 1, shift by 2, shift by 3. So this bit 0 goes here, and bit bit 1 goes here, and bit 2 goes here, but this bit like instead goes here, and this bit goes here, and this bit goes here. So they all like shift in a circular way. So now if you go back to our code, you can see that we can implement circular shift by either combination of slides and of concatenation, or by ORing results of shift operation. And you can see here that actually first syntax is kind of easier to read than the second syntax, because with shifts you need to, because with shift operation it may be more difficult to follow. Like sometimes you need to compute in your mind which bits goes where. Now with uh, okay, so this is a circular right shift by n. So we were doing circular shift to the left, and now we are doing a circular shift to the right. So this is Philip's solution: a s1 s minus 1 0 n minus 1 s. Right? Okay.
are you
So
just
s
playing the code? I can't see it.
wait. Yeah, I think I did share incorrect way. Okay. Okay. So So this is a Philip solution. So let's see, golden solution is in circular shifts. So S minus 1, 0, N minus 1, S. S minus 1, 0, N minus 1, S. Yeah, this is correct. So now, if we, okay, and here is A shifted by S or A shifted by N minus S. Actually, this solution I wrote. It's not Michael of Kuskov. Yeah, A shifted by S, A shifted back by N minus S. Okay, this is correct. Okay, now arithmetic shift or sign divide by power. Yeah, there is such operation as arithmetic shift, and the difference between logic shift and arithmetic shift is a treatment of the highest bit. So if we let me share. Okay, so let me share this like graphic thing. So basically, so how to erase everything here. Let's just do new one. So
it, and sorry, Mr. Yuri, I gotta go,
yeah.
but I want to say thank you for the warm welcome for the beginners guide. I really
Yes,
appreciate
sure.
that.
Yeah.
Just want to say
Just like
thank you a lot.
yes. Okay. So just like try with the board and send email once you have questions. Yeah.
Okay, okay.
Okay. Thank you. Okay. So now with arithmetic shift.
Get
So
the error
now with arithmetic shift. Okay. So can you see it?
by declaring it as a sign. That's what makes it an arithmetic shift. But why do you have to use 3 right arrows instead of just 2?
No, if you declare it by sign, unfortunately, if you use regular shift, it still acts as a shift.
Why?
This is not because this is not C. In C, if you declare signed integer and unsigned integer, then shift operation acts differently. For unsigned, it uses logic shift, and for signed, it uses arithmetic shift. But in Verilog, for some reason, they standard committee decided to do it different way.
You know why? Because it sounds absurd.
No, not necessarily, because sometimes you want to do logic shift operation.
Right, but if you're declaring the variable signed, then it seems like clearly you want the sign bit to act like a signed number. So
We can actually get Icarus Verilog, and we can see what Icarus Verilog is doing. in different cases.
Guys, the
So
syntax
let's
is
see it.
more
Yep.
different. See, I mean, this was derived from C, right? First they had C, then they came out with the Verilog. Verilog is supposed to be imitating C, so why would they
But in Verilog there were no signed numbers up until year 2001. So
Okay.
all vectors were considered bit vectors. Even now in industrial code, signed is a very rare thing. Usually, just unsigned numbers everywhere, and that's it. Oh, yeah. So let's actually see what happened in a Verilog with the different operations. Like you see here here uh, uh, like you can use signed, but if you don't use signed, okay, this is actually a good question. Let's see what happened with modern syntax in Icarus. So let me share console. Restore. So basically, every time you have questions like this, the best way to resolve such questions is to like experiment with the different numbers. So let's get a scratch. Say t.sv. So let's get like module m, and then let's put like logic 70a. Like let's put unsigned, and let's put logic signed. Logic signed 70 signed. So let's put initial.
Can you display what you do? There, good.
Huh?
Okay.
I am just declaring two variables. So do you see it?
Mhm.
I'm just declaring two variables. So one variable is unsigned, which has a type logic, and another variable is signed, which is a signed type. So now what we are going to do, we are going to assign different values to this variable, and we can see what is the result of logic and arithmetic shift operation. So yeah, let's make it not 70, but let's make it 30. So to have like 4-bit value. So now suppose we put u is equal 0, 1, 1, 1, and we put like u is equal u shifted by 1. Okay, do dollar display b u. Okay, so first we are getting so first we are getting number positive number, then we are getting negative number. See what happened, and then we are doing the same thing with with arithmetic shift operation, and then we are doing the same thing with a signed number. So like instead of U, we put S, right? So let's see like all the different combinations. So first we got a positive number shifted by 1, then we get negative number shifted by 1, then we are using arithmetic shift for positive number, and we are using arithmetic shift for a negative number. Then we are doing the same thing for signed numbers. Okay. So now what we do is that we are doing Icarus Verilog. Sorry. We need to do Icarus Verilog with G2005 SV with an option to just show that this is SystemVerilog. 42 syntax error. What is the syntax? Oh, and module. Yeah, okay. Then we are doing VVP A out. Okay, so you can see what we got. So we got that for so let's get this code. Let's get this code and let's see what we got with our code here. Okay. So if you get a positive number, and if you shifted, wait a second, it printed something wrong. Okay. What?
Yeah, it seems out of phase.
Ah. 1 second. So let's actually put what we are trying to print. So we are putting this is 1, 2, 3, 4, signed 1, signed 2, signed 3, signed 4. Oh, sorry. This actually we need to put this as 4-bit number, because if this is not specified, this is actually a frequent, not frequent, this error, as you can see, it can happen unless you specify 4B. That number is considered like as a decimal number, and in C it's actually considered as an octal number. So all numbers which start from 0 are considered octal number, and like 1111 is considered as a decimal number, and now you assign it to 4-bit value and it just get cut. So that's why when we specify binary number, we need to put the size of this number, and then we need to put ampersand and B. Okay. Now let's do the same thing again. So we compile it. Yeah, so now it's a different story. So now you can see what happens, that if you had 0, 1, 1, 1, it became 0, 0, 1, 1. Now if you had 1, 1, 1, 1 shifted by 1, you can see that it added to like on the left, it added 0. So which is a logic shift, not arithmetic shift. Now, if you use arithmetic shift with unsigned number, then it acts in the same way as a logic shift. So it put 0, 0 to the left and it put here 0, 0. So with the unsigned number, logic shift and arithmetic shift does the same. Now, but with a signed number, if you do if you do a logic shift, like of a positive, it does what we expect, which is 0, 0, 1, 1. But if you do logic shift of a negative number, and this is a negative number, it prints you 0, 1, 1, 1, so it's not considered this number as signed. However, if with signed number you are using arithmetic shift, then it does prevent sign. So it effectively multiplies the uh, leftmost bit and propagate it multiple times. And by the way, if this is even more visible if we try to shift not by 1, but if we try to shift by 2. Oh, sorry. So if you shift it by 2, to remove the thing. So if you shift it by 2, you can see that in case of a logic shift, it always adds zeros. But in case of arithmetic shift of a signed number, it gets sign and it propagates sign to the right. And the reason they did it in a standard and not following semantics of C is because in Verilog originally the only signed number was a type integer, which is 32-bit signed number, and there were no signed bit vectors, so they put signed bit vectors only in year 2001, and probably they wanted to keep signed bit vectors with a regular shift operation behaving as it was behaved before. So this is the reason they had to create a new operation which actually acted with signed numbers in such way. So, but this is how they decided to put in a standard.
So when you do
And
this shift with the 3 arrows, it always takes the signed bit, even if it's an unsigned number. Either way, it always propagates.
no, with unsigned number, it thinks that because the number is unsigned, that bit is not assigned, and there is no point in propagating bit leftmost bit, because that bit is not assigned. That bit is not assigned. So this is just how they choose to do in a standard. This is a relatively late addition to the standard, and not all engineers know it, because in most of industrial code operates with as unsigned bit vectors. Yes, so see, we have to learn it to be familiar with that arithmetic by like a trial and error. And the best way to do trial and error is to make such small pieces of code and to simulate it with the Karus Verilog. Yeah, so now, and by the way, here, instead of this like bit vectors, you simply can put like let's say 7 and -1, and the result will be the same. So you can put like 7 and -1. So you can put -1, 7, and this kind of more intuitively understandable. -1, 7. Yeah, 7 -1, 7 -1. Yeah. Okay. Yeah, you see, same thing. Okay, so let's go back here. Okay, so this is let me stop sharing this and let's start sharing this window. Okay, so let's go back to yeah, and the reason we need to use arithmetic shift is because arithmetic shift is a way to divide by 2. So if you have unsigned number and if you want to multiply it by 2, this is equivalent to shift to the left. And divide by 2, this is equivalent shift to the right. But if you are dealing with the negative numbers, then by shifting number to the left and to the right, it's in order for this shift to work, you need to propagate sign. So basically, we can create a little program again, which is so let's share the previous screen. So if you go back here, so let's for comparison divide this number by 2. So let's put instead of shift like let's put instead of shift, let's put division, right? So and let's remove so let's put divide by 2 signed and divide by 2 unsigned. Yeah, so let's do it again. Yeah, so you can see that divide, but you can see that actually divide by 2
Not seeing any change.
behaves differently. Divide by 2 behaves differently because so divide by 2 is not equivalent to shift because in unsigned, so in unsigned it does work as a shift to the right, a logical shift to the right. But in signed number, it produces 0. And in signed number, it produces 0 because -1 divided by 2 is actually 0. It truncates to 0.
Did you just display that and it's not on the screen? I mean, did you just change the program and then run it? And then we
Yeah.
don't, right now, we're still seeing the old one with the shift operators.
Wait a second. I'm not sure what you see. Okay, let's do it again. Maybe it didn't. Okay, so do you see it now?
Still seeing with the two, with the double arrow and the triple arrow shifts with signed and unsigned. Nothing with the multiply or divide.
Wait, do you see black screen or white screen now?
Black screen.
black screen.
Mhm.
Wait a second. There is something wrong with display. So do you see my sharing operation? I mean, do you see division operation now where
No.
where I highlight?
No. It's still back. It says at the top, scratch / AAA. A,
Yeah.
and then it's still showing right shifts.
No, I'm showing this part. So do you see this with division? So I didn't erase shifts to the top. I just like added code to the bottom. So let me put here like dollar display.
Nothing's changing on the screen for the last 3 minutes.
This means this is bug in this bug in Zoom. Let me figure out how to what to do about it. Just a second. Nothing changes for you now?
Nope.
Okay, let's do stop share.
Okay, and that changed it. Now it's back to just the videos for everybody there.
Okay, so what do you see now?
Just the videos of every. There it goes. Now you just changed it.
Okay, so now do you see division operations now?
Yes.
Okay, so now if you put these numbers and if instead of shift is a logical or arithmetic shift, we use a division operation, you can actually see that division for unsigned acts in the same way as a logical or arithmetic shift to the right, but division for negative signed doesn't work like this. If you do -1 divided by 2, it actually creates 0. While in a while with arithmetic shift, it would create -1. And if you get some like different numbers, so let's get instead of -1, let's get number, let's say like -5. So and let's see what it produces with a -5. So let's replace -1 with a -5. And run it again. You can see that -5 shifted arithmetically produces -2. So but -5 but -1 produces 0. So 1 1 1 1 is a -1 and 1 1 1 1 1 0 is a -2. So now for number like a -5, it like it goes to 2. However, if you put -4, a -4, in this case, okay, -4 is 1 1 0 0, right? So with the arithmetic shift is also doing -2. Yeah, so like -1, all so -1 has this problem, but -4 doesn't have this problem. So you need to be like aware of these differences between logic shift, arithmetic shift, and the division and the multiplication operation.
Yeah, but what's
So
the
if
concept?
we put here,
What's the concept? It seems
yeah,
like sign doesn't operate like you would expect with division. I mean, it was a
but
little.
this is how it's implemented with two's complement numbers. So
I know.
this always was like that. This is not Verilog specific. You see?
Okay. All right.
Yeah, this is not Verilog specific. So you can see that if you use like if you use 4, so if you get like if you shift oh, wait a second. Oh, here we actually divided this by 2. So oh, sorry. This is actually my mistake. I thought that we got no, this is fine. We divide wait, sorry. I did stupidity. I was doing shift by 2, but I was dividing by 2 and we need to divide by 4.
Mhm.
Sorry. It's just I'm doing some like goofy things. Okay, so now let's compare with divide by 4. So let's get -4. Let's get -4. And let's divide it. So let's get -1. Let's get so we were dividing this by 4, but now let's divide it by 2. So dividing by 2 is divided by 2. Yeah, let's leave divided by 2, but let's this was divided by 4, sorry. Divided by 4. So let's compare division by 2 with shift by 1. Shift by 2. Shift by 1. Yeah, okay, so we are getting number which is either 7 or -1, and we shift by 1 or we divide by 2. Yeah, so you can see that those operations are different, because if you do if you do arithmetic shift, you are getting 1 1 1 1, but if you are doing division, you are getting 0, which is actually makes sense. So now if we put not -1, but if you put -5, so if you put -5, yeah, so like if you put -5, then you are getting with so with a logical shift minus you're getting 1 1 0 1, because -5 was 1 0 1 0, right? But here you are getting -2. So actually with a logical shift 1 1 0 1, what is this value? Just a second. It's a 1 0. Yeah, this is -3. So with logical shift you are getting -3, but with division you are getting -2. So actually to convert sign division into arithmetic shift, you need to add 1. Yeah.
So this,
Yeah, but those are some arithmetic details you need to be aware when you are dealing with a signed number. But anyway, here we can see that this
getting the sign bit into the number. When you go with the divide and multiply, you're not getting the extension of the sign bit down into the other bits.
no, you are getting the extension, because with a signed number, if the signed number is a large,
It's nothing to do with large. It has to do with the sign number is shifting. It's not shifting the sign bit into the low order bits. It's just doing you the numerical operation. So
Yeah, it does numerical operation, but you can implement this numerical operation by a combination of it's not doing it's not doing it's not doing just arithmetic shift, but you can implement it with a combination of arithmetic shift plus one. So you can do it this way.
So the sign, when you use the multiply and divide, it's kind of keeping the sign bit and the other bits separate. It's not,
You can implement it as a separate. So if you want to implement signed division, you can change the number signed, do division, and then like put a sign back, or you can use a combination of arithmetic shift with like addition of one. Yeah, but anyway, let's actually move on, because this is all details of arithmetic. Also, they're useful because people who look how binary arithmetic works, they need to study this in details. Yeah. Now, yeah. So next is arithmetic right shift. So let me go back. Okay, so here is example. Okay, so now second thing is to implement right shift by arithmetic right shift of n by s using concatenation. Yeah, so Philip here put 3 times a n minus 1.
I think we're
But
looking,
actually,
we're
huh?
seeing we're
Do you
not
see
going
it?
back to Philip's code. We're still seeing this shift with the multiply and
Okay,
divide.
let me do it again. It's some, I don't know, Zoom network optimization or something. Okay, so do you see now browser?
No. Yeah, now we do.
Yeah, okay. Okay, so here Philip put 3 times this highest bit, so a n minus 1, a n minus 1, a n minus 1. This can be done with a more short syntax. Yeah, so you can put the following syntax. So the following syntax in Verilog allow to repeat one bit like s number of times. So you are getting highest bit and you repeat it s times. Yeah, and by the way, I probably shouldn't call this thing arithmetic shift or sign divide by arithmetic shift or sign divide by power of 2. I need to actually change description of it to reflect what we just discussed, because this is not a signed divide. This is to make it signed divide, you need uh, to add +1 to it. So now so what Philip wrote here is correct, but you can use a shorter syntax. So you can just duplicate n minus 1 3 times.
The thing with the brackets is your concatenation operator.
You're talking about
With all,
this one?
yeah, that line.
Yeah,
That's
so generally in generally in a Verilog, the syntax to concatenate A and B is square bracket A comma B. But if you want to replicate A n times, you write n and then you put without comma in square bracket A. So this syntax means replicate A n times. So if like n is equal 3, this is the same as putting A comma A comma A. You see? So if you write like 3A, this is same thing. But if you write like A comma B, this means it got bit vector A and concatenate together with a bit vector B.
So it's shifting and ORing the bits.
Yeah, so in a software it's implemented by shifting and ORing, but in hardware you just get bunch of wires and you put one group of wires and put together with another group of wires.
Hmm.
Yeah. Okay, now let's go next. So next is using such a for loop. So we have I if I is more than s plus 1, then use a n minus 1. Otherwise, I plus s. Okay, this looks
Line 16.
this looks okay.
On line 16, what's the significance of the S at the end of the concatenation? Where it says colon.
So the significance is that we cannot put 0 there, because if there is a 0 there, we are not going to shift anything. We need bit s to become bit 0.
So why is it
So
on the left
let me
side? Why is it the S on the left side of the square bracket instead of the right side of the square bracket?
wait. You're talking about line 16?
16. Right. Why is it not the left part? Why isn't that left square bracket on the left side of the S? Why is not the S on the right side of the square bracket? Why is it not?
Oh, because this is a bit slice. This is a bit slice. So we are this syntax like A M N just means that we are getting slice of A from bit M on the left to bit N on the right.
Right.
So like basically if you do something like 1 0 1 0 1 0 1 1 like 1 1 1.
Mhm.
So this is how your bits look like. So let's put 9 8 7 6 5 4 2 1 0. So let's like remove. So 1 is bit number 0. This one is bit number 1. This is, oh, sorry, I'm not showing you the right screen. Or do I show?
Yeah, it's showing.
Yeah, okay. So here is a bit number 0, bit number 1, bit number 2, bit number 3, bit number 4,
Mhm.
bit number 5, bit number 6, bit number 7, bit number 8, bit number 9, right? So basically when we write, like suppose that like n, suppose we put 5 3, right?
It's 5 through
So if
3.
you put 5 3, this is the slice. So
Mhm.
if you put 5 3, this 5 3 will be equal to 101.
Okay, so now go back
So
to
we are
that.
getting it from the middle. So
Mhm.
essentially when we write like let's say like a like s plus 2s, uh, so this means that again suppose like s is 5, so this is 0 1 2 3 4 5, and s plus 2, so we are getting like um, 0, we are getting this 101 from this section and just shift it to the right. So now bit number 5 became bit number 0.
Okay.
So this is how bit slices work. Yeah. Okay. So now, so we are getting that if I is more than s plus 1, uh, then you put a n minus, no, here it should be not s plus 1. Here it should be n minus s, because we are getting n and we are subtracting s, and this is where all signs should be propagated. So if we look to the golden, you can see that here, if I is more than n minus s, then we put leftest sign bit, and otherwise we put I plus s. So I plus s means that new bit 0 is actually old bit s, and new bit 1 is old bit s plus 1, and new bit 2 is old bit s plus 2, and so on and so on.
This is gonna take a while to get used to. Why didn't they just stay the way C does it? You know, just left shift and then hand out the bits.
Because C is not intended as a bit vector processing language. C is intended as a software language which works on a computer with some standard word size. It's a language which operates either with like 16-bit or 32-bit or 64-bit numbers, but not making some weird numbers like 13-bit number with a 7-bit after digital dot. So in Verilog, you're constantly dealing with some weird kind of numbers, because you need to spend only some number of bit for a flip-flop. Like if you create a counter which can count from 0 to 15, you need to use 4 bits, because you need to use 4 flip-flops. And if you use 32 flip-flops, you're wasting power, and you cannot scale it. If you put 32-bit everywhere, you can only use like 3-bit or 4-bit, then your processor will be 10 times larger. So in Verilog,
C.
those bit slices are everywhere.
It's just taking me a
And
while.
basically, it's easier. Basically, if you don't have concatenation operation, so instead of writing A, B, C, you have to write something like A shifted by shift A, or B shifted by shift B, or C shifted by shift C. You see,
Right.
and like it's obvious that this syntax is much shorter than this
But
syntax.
it's easier for me to understand the bottom one. Because I'm so
Yeah,
used
but
to
this is easier. But this is easier because you got used to C, which was around for the last 50 years. You
right.
know, but we suddenly getting used to concat syntax is actually easy to understand in most places.
Okay.
Now, yeah, so here we have to put n minus s, okay? And yeah, so here we need to change this expression, and here n minus 1 is correct, but here I plus s is correct. So now if you do the same thing using generate, yes, this is the same mistake. So for generate, you need to check that I is more than n minus s. Yeah, those like bit operations are like painful, and like as you can see, like I myself getting confused with it from time to time. But this is something like everybody needs to do exercises, because um, um, this is something which happen in code a lot, and you need to write such expressions with concats and bit slices. Plus, with these exercises, you can be trained on writing a for loop inside initial blocks and inside generate blocks. Yeah. Okay. So Philip, is this all you did in 04 so far?
Yes, I'm still working on pipeline examples.
Yeah. A pipeline example is like next thing. Yeah. Okay. So in this case, we are finished with this today. So we discussed arithmetic and shifting in 04. Yeah. So please fix mistakes with putting s plus 1 instead of n minus s. Yeah.
Yeah,
So
I'll
do
fix.
you like understand why this is not going to work if you change the size of bit vector?
Yes, I'll fix that.
Yeah, okay. So I think this is fine. So what else do we have today? Yeah.
Philip,
So if we
you were talking to Philip.
look, I'm talking everybody. So like are there any other questions for today? So today we went through
Yeah, really didn't
a part
understand
of
that
Philip
bit, but
homework, and
I didn't really understand the last bit between the two methods, but I had good experience the week before last using Chat GPT to help me understand this stuff. So I think if I run it through Chat GPT, I can get it to explain.
in Verilog chat GPT is making very stupid mistakes. I don't recommend
Right.
doing it. Can tell you something absolutely totally wrong, and it will just stick to it. Instead of chat GPT, I recommend method which I just demonstrate to
But
write
it's easier than going
short
through trying
program
to find
for
it in the net,
Icarus.
right?
Huh?
Try to understand the syntax of the language. It seems like it's easier to have ChatGPT teaching the syntax.
It doesn't know Verilog.
Huh? It does. It seemed
Chat
like it.
GPT, Chat GPT frequently puts pieces of C in Verilog,
Oh, really?
or just uses, yeah. So it mixes languages, and this looks really stupid, but this is what it does.
Right.
So basically, it will just very confidently tell you uh, wrong thing, and then you will use this wrong thing. So don't do it. It just
You want to
not at
quickly
the level.
concept between those two blocks.
Huh?
In the example
You
is
want to
Philip.
ask ChatGPT about difference between generate and let's ask and see what it says. So let's do experiment.
All right.
So let's do experiment. Let's formulate a question. Maybe it already knows. Who knows?
I was
Okay,
able to
let's do it.
examples and it seemed to understand.
So can you formulate the question? Let's formulate the question. I personally don't recommend using ChatGPT. I recommend just testing yourself with Icarus Verilog if you have problem with arithmetic.
Right, but the problem is you have to be able to you have to be able to parse the code. And to be able to parse the code, if you're so used to C, it doesn't make any sense. Whereas ChatGPT is good, like for learning, like for example,
Chat GPT doesn't know Verilogs. This is a problem. Okay, so what? So let's share the screen. What do you want to ask GPT? 1 second. Yeah, Danish is asking, have you heard about Prim IS AI Rapid GPT? Never heard. And I don't think it makes difference in this case because right now those tools simply don't know details of the standard. Okay, so let's get ChatGPT. So can you formulate a question?
Me?
Yeah. So
Well,
you were asking like what is the difference between always comb and generate in system
doing is
Verilog, right?
taking your examples and then asking it questions about the examples that you were doing. So I was using it.
Let's ask.
So if you'd say like the one we just did, right? The you can seem like it was helpful for learning the language to me.
So you want to formulate a question?
Well, what I was doing is taking one of your examples, like the one that we just went over from Phillips, and cut and pasting it into ChatGPT and then asking it questions about the code. You know, like what does this code do at line 55? Right? That's the kind of way I was using it.
Let's okay. Let's try to do it. So you want to
Like the one we were just doing.
copy and paste what code?
Okay, that one. It's fine. Right.
Which
So
is
if I,
this one?
yeah, so if you cut and paste it in, and then you can say what's going on in line 4, and then explain that line 4 to you.
Just a second.
It seemed like it was working.
Just a second. So let's see. If it helps you, uh, if it helps you, you can use it. The problem is that I tried chat GPT asking to write something and it was writing using some pieces of semantics. So I would be very cautious to use it for learning Verilog because it doesn't know Verilog. Okay,
Mm.
now this module is declared. It has input port. Close signed wire. Necessary arithmetic requires signed operand. Okay, yeah. Performs arithmetic shift. Okay, so what?
So for explaining the language to you, maybe it's fine. Maybe just if you give it a complicated piece of code to write that it mixes up with C.
If it works with you, uh, it's okay. Just I personally wouldn't do this because it was putting really stupid designs in the past for me.
Well,
Like
the
when I
alternate
tried
is
it.
to go back to the book and then find it in the book, and that seems like it takes a lot longer.
You can conform it with the book, but I wouldn't trust chat GPT as like final authorities for sure.
Mhm.
Because like I can show some conversations I had with chat GPT. Let's see. Let's get some history because it keeps history.
I thought
Uh,
GPT throws away your history every time you log out.
no,
No?
if you have account, it doesn't.
Oh, really?
Okay. Yeah. You see here. Okay. So let me show you some. So let me show you something I did in the past. Uh,
How much does an account cost?
well, uh, actually, I think you can do it for free. I'm using a free version. Okay, so this is something. Yeah, things like priority encoder, it simply get it from somewhere. By the way, this is not correct. Oh, but this is not correct. Okay, 1 second. Let me find.
That's Rust code.
No, this actually Verilog code. I was like testing something. I wanted to find. Convert to 2003. Second.
It's funny, I asked ChatGPT if it would save the information for me, and it said it can't. And then yet you're
No,
saying
it saves it for me.
but
Just
when
I
I
want to find example. Just I want to find example where it put something like truly stupid.
Hmm.
I think I put it before I created accounts there.
but I have an account, I log in, but when I asked ChatGPT if it could remember the conversation, it said it can't do it. And yet seems like you've got a list over there and context centers remembering it.
Oh, yeah,
So
yes, it does. It does have memory. It does have memory. So pointer down circular buffer. Yes, anyway, if I will find, I will show it to you. But the thing is, it was creating non-synthesizable code, and it was doing like code without reset and stuff like this. So I wouldn't trust Chat GPT with the Verilog.
okay.
Especially when you go to next stage, which is microarchitectural elements.
I'm still
Then
fine.
what it's doing, it's just so wrong. Yeah.
Hmm.
Okay. Anyway, so yeah, but for explaining to you things like ports, continuous assignment, you can certainly do it. But if I were you, I would recheck it together with a textbook or with a standard, preferably standard. So maybe read first from ChatGPT and then go to text of standard and check it with the standard.
Right. Seems like ChatGPT is a quick way to get the idea and then always go back to the books to verify things.
Yeah, something this. Okay, so is there any other topic for today? No. Okay, in this case, like talk to you next week, and I think next week I will make uh, a meeting in Hacker Dojo and do some work there with the boards.
Okay.
Yeah. Okay, so thank you everybody. Yeah. Okay.
Sorry.
Bye.